Okay, here we are. We're going to take a look at 12.2 now, and that are tests for independence and homogeneity. So we're going to take a look at 12.2 now. We're going to interpret some contingency tables. We're going to perform the test of independence and perform tests of homogeneity. So let's take a look at interpreting the contingency tables. Here, do some college majors require more studying than others? Good question. I know when I was in college, it seemed like you never saw the nursing majors because they were studying all the time versus some other majors who were not. So this is wondering if some majors require more studying. The table shows the results from the National Survey of Student Engagement Survey, where 1,000 college freshmen were asked their major and the average number of hours per week spent studying. This is called a contingency table. So here's your hours of studying per week. Here are some of the majors. So contingency table relates to two qualitative variables. One of the variables is called a row variable, one category for each row of the table. The other variable is called the column variable, which has one category for each column of the table. The intersection of the row and the column is called a cell. The total number of individuals on the table are 1,000. That would be the grand total of all these added together. Let's look at our tests of independence. We are interested in determining whether or not the distribution of one of these variables differs depending on the value of the other. So, if the variables are dependent. If the distribution of one variable is the same for all the values of the other, then the variables are independent. So does it really matter what their major is? Does that affect how much they study, or is it just how much a person likes to study in general? So in the or some other confounding variable, I shouldn't say that, so I don't want to give a cause. But in the survey about the major and the hours spent studying, if these variables are independent, then the distribution of hours studied will be the same for all majors. So the distribution of majors will be the same for all categories of hours studied. So here we have it again. Let's take a look. So we're going to conduct a test to determine if the two variables in the previous study about the student majors and hours spent are independent. The null and alternate hypotheses would be, the null hypothesis is hours studying and the major are independent. And the alternate is going to be the hours studying and the major are not independent. So we're going to use a chi-square statistic to test the null hypothesis that the hours studying and the major are independent. If we reject it, then we conclude that the variables are dependent. So the null hypothesis states that the hours studying and the major are independent, but by using the multiplication rule for independent events, we can compute the expected frequencies. So we have, for example, we have the number 0 to 10 hours of studying humanities times the probability of being a humanities major. So here we have our 345 for our humanity, and then here are the hours of studying total. Now we obtain the expected frequency for those who study 0 to 10 hours and are humanities majors by just multiplying these together to get the grand total. So when we multiply them together, and we're multiplying by 1,000 to get the expected frequency, because that's the number that we have, what we will get here is 88.665. So again, we're multiplying these two together, and don't forget then to multiply it by the number that are in the study so that you can get your expected frequency, 88.665. Now, from the previous example and applying some arithmetic, we can see the expected frequency can be obtained by the following formula. The row total times the row or the column total will be the divided by the grand total. Sorry. So basically what we're saying is that two of these will reduce, and went back to the previous slide. So if you just have this times this over your 1,000, you will get it. row total, column total over grand total. So the expected sequences for all cells, or the number of individuals you would expect to find in that cell, the assumption that the two variables are independent. If the differences between the observed and the expected frequencies are large, then we're going to reject the null hypothesis of independence. So we're going to state the null and alternate hypotheses. We're going to compute the row and column totals. We're going to compute the expected frequencies using the formula we just figured out, and we're going to check to be sure all frequencies are at least 5. Then we'll choose a level of significance and compute the test statistic using the chi-square statistic. Find the critical value from table A4 using R minus 1 times C minus 1, that's row minus 1, times column minus 1, degrees of freedom, where the number of rows and columns are R and C. If chi-square is greater than or equal to the critical value, we'll reject the null hypothesis. Otherwise, we will not reject the null hypothesis. And then finally, we'll state the conclusion. So we'll perform a test of the null hypotheses that a major and hours of studying are independent. So here we're going to use alpha at 0.01. So got to have a lot of evidence again for this alpha number. So here we have again our chart. We're going to say that the null hypothesis is that they are independent and that the alternate is that they are not independent. Compute the expected frequencies. First we're going to compute the row and column totals. We compute the expected frequencies as an example. Let's look at the expected frequency for the cell corresponding to the business major. So let's take a look at the business major here. Studying 11 to 20 hours, that would be this cell. The row total is 430. The column total is 309. So we're going to take those two, multiply them together. This dot should be up here in the middle. Multiply them together, divide by 1,000, and the expected frequencies are given right here, 132.87. So when we do that with each one, we will get the following expected frequencies. So now we're going to take the number that we had and we're going to multiply it by those expected frequencies. So we're going to take the difference of each one and then square it, divided by our expected. So this is our chi-square statistics. So here we have, again, our observed and our expected. So we're going to take observed minus expected, square that, and then divide it by our expected. After we do that to each one, we're going to add them all together, and when we add them all together, we will get 34.638. So once again, observed minus expected quantity. After you do that difference, you're going to square it and then divide by the expected. After you do that to each and every one of these, you're going to add them all together. Okay, so from the first one to the last one, then we add them all together and we will get 34.638. Now we're going to compare this number. There are 3 rows and 4 columns, so the degrees of freedom would be our 3 minus 1 times our 4 minus 1. So remember, here the degrees of freedom are a little bit different. So we have 3 minus 1, 4 minus 1, and that will give us 6. So from the table A4, we find that the critical value corresponding to 6 degrees of freedom at 0.01 is 16.812. Now, we found that the test statistic to be 34.638. So since it is bigger than what we have, then we're going to reject the null hypothesis, and we conclude that the choice of major and the number of hours spent studying are not independent, that the number of hours the student studies varies among majors. So keep in mind too that we used our 0.01 statistic. Now, if we would have used our 0.05 statistic, will we have gotten a different value? We don't see it on here, but we might want to take a look at that in another trial just to take a look at it if it has a confidence level of 95% or not. But here it certainly does not meet the 99%. All right, so we can do this on the TI-84. We have our test. We go to our chi-square test by pressing stats. This procedure requires the observed frequency to be entered into a matrix. So we'll perform a test that major hours of studying are independent. We're going to use our alpha as 0.01. We begin by entering the values into matrix A. We press stat and highlight the test menu, select the chi-square test, and then enter the A values in the observe field, then press calculate. Now the p-value is 0.000005, which is less than our 0.01. So we would reject the null hypothesis and conclude that the choice of the major and the number of hours spent are not independent. The number of hours that a student study does in fact vary. Well, maybe not in fact. We believe it varies among majors. Might be some other confounding variables out there. We're not sure. So here we have it. Now we looked at before. Okay. Now, objective 3, we're going to perform tests of homogeneity. I'm not sure why I'm having trouble saying that word today, but anyway, in the contingency table we've seen so far, the individuals were sampled from a single population. For each individual, the values of both the row and column were random. But in some cases, the values of one variable, let's say the row variable, are assigned by the investigator are not at random. In these cases, we consider the rows as representing separate populations, and we are interested in testing a hypothesis that the distribution of the column variable is the same for each row. This is a test of homogeneity, and I really, homogeneity, there you go. Okay. So in a test of homogeneity, we are testing a hypothesis that the distribution of outcomes is the same for each row. The method for performing the test of homogeneity is identical to performing the test of independence, so nothing new. So the test hypothesis of the outcomes is the same for all 3 treatment groups. In the example about the drugs of, now they give me these names, telmisartan and ramparol, and we're going to use an alpha at 0.05 level. So the null hypothesis says that the distribution of outcomes, fatal heart attack, non-fatal heart attack, no heart attack, is the same for all the drug treatments. The alternate hypothesis says the distribution of the outcomes is not the same for all the treatments. So we're going to use the row and column totals to compute the expected frequencies again. The expected frequencies are follows and we see all of the frequencies are at least 5, so we can proceed. Following table shows the observed and the expected frequencies. Here they are. Here's the observed and the expected. Now we're going to use these to go into our chi-square statistics for all of them from the beginning to the last. We're going to add them all together and we get 2.259. Now, there are 3 rows and 3 columns, so when we're figuring out the degrees of freedom, we subtract 1 from each and then multiply, and we get the degrees of freedom of 4. So from table A4, we find the critical value to 4 degrees of freedom, and alpha at 0.05 is 9.488. So since now we can conclude that 2.259 is smaller than 9.488, we're not going to reject the null hypothesis because there's not enough evidence to conclude that the distribution of outcomes is different for the different drug treatments. So there you go. So you should know how to interpret the contingency tables, how to perform tests of independence, and how to perform tests of homogeneity. And that is all for 12.2. We're going to jump back to chapter 4, and I'll see you for that.